In this video I will discuss classification and classification statistics in the context of latent class analysis. Based on the estimated parameters of a latent class model, it's possible to determine to which class each individual belongs. When the latent class model is used for clustering of diagnosing, then it's relevant to be able to classify individuals. The model building stage is then just the first step. Classification is also relevant when you want to show how classes are related to other variables using a three-step approach. The three-step approach will be discussed in one of the next videos. In this video I will show how this classification works. I will also discuss classification statistics, which quantify how good the classification is, that is, how certain we are about the class assignments. The latent class model yields information on the probability of a certain response pattern, the probability of y, given the class membership. The probability of a response pattern given class membership. That's what you see here. And for classification, we need the reverse probability. We need the probability that someone belongs to a certain latent class, conditional on the response pattern. Well, it's well known that the prediction can be reversed, which is what we need here. Instead of predicting y from x, we want to predict x from y using the Bayes rule. And the Bayes rule, let's say in general terms, is written out here. And so if you want to know the probability of b given a, and you have the probability of a given b, then you can transform the probability of a given b into the probability of b given a using this formula. And so by multiplying the probability of a given b by b, and then dividing by the probability of a. Let's see how this Bayes rule works out in the case of a latent class analysis. And so what we want is to obtain what we call the posterior membership probabilities, the probability of class membership conditional on the responses. If you apply the Bayes rule, let's say the b given a obtained from a given b, and so that apply it here. So the probability of b given a, and here you see the probability of a given b, which is now the probability of the y's given the x. And so we multiply by the probability of being a certain latent class and divide by the overall probability of the response pattern. In fact, these probabilities should be familiar to you, because these the product that you see here in the numerator is also in the, let's say, the first formula defining the latent class model, the mixture formula. And here you see the overall probabilities, which is obtained by, let's say, summing the mixture over the latent classes. So what I did here is I filled in actually the different terms for the probability that you see here. So I write now the probability of a response pattern in terms of the local independent assumption, and I write the probability of a full pattern as a sum over latent classes, and then put in, let's say, the full equation of the latent class model. So this is the way we can obtain what we call the posterior class membership probabilities. So once we have the posterior class membership probabilities for every response pattern or for a particular individual, we can determine to which class a person belongs. And the typical way of doing that is using what we call a modal classification rule. So we select the mode, which involves assigning every individual to the class for which the probability of being in the class concerned is largest. To make this more concrete, let's look at a numerical example, and later on I will show you how to do this kind of computations also with concrete numbers. But for this purpose I will go to LatentGOLD and run the 3-class model with the GSS82 dataset. I open the dataset, I will select the 4 indicators, set them to be nominal, do a scan, that's all kind of routine for me, and then specify the 3 cluster model. Well, new compared to what we have been doing so far is that we want to see the classification outputs. In the output tab, I will ask for the classification posterior output. Well, the classification output for the GSS82 dataset, it looks like this. What you see here is that for every possible response pattern, for example, the mostly true, interested, good purpose pattern, you get information on how likely it is to belong to each of the latent classes. So this is the probability of being in class number 1, conditional on a response pattern, the probability of being in class number 2, and the probability of being in class number 3. The modal class is a class for which the probability is largest, which in this case is the first class. So you see the numbers, let's say for this pattern, that we compute using the formula that I showed you in the, let's say on the overhead sheet. What I will do now is show you how we obtain these numbers from the profile output. Because there's a direct link between the numbers that we get in profile and these probabilities, which is also what you could see here in this equation, because this number is in the profile, these numbers are in the profile, these numbers are in the profile, these are in the profile. So basically, if you collect the information in the profile in the right way, you should be able to get the probability of it being in a certain latent class for a particular data pattern. What I'm going to do is compute the posterior membership probabilities for the first pattern. So what I need is the following. I need the cluster proportions, because they enter in the posterior probability formula, and I need the probability of giving the mostly true response in every cluster, the interested response in every cluster, and the good response in every cluster, and the good purpose response in every cluster. Because that's the pattern that for which I'm going to compute the posterior membership probabilities. And I can copy these, and that's something that I already did, and then I will paste these in this spreadsheet. And so here you see the cluster proportions, the cluster sizes, and here you see the conditional probabilities of the response concerned for each of the classes. That's obtained from the profile. Well, the first step in the in the computation is that we need to obtain this number, the probability of a full pattern conditional on the class. So then I will let's say multiply that by the class proportion. If I sum that over all the classes, I get the probability of the pattern concerned, and then I do the division. So here you can see I multiply the probability of the response concerned for all the responses. This is then for class number 1. I do the same for class number 2, and do the same for class number 3. What you can see is that the all 1 responses, the mostly true, interested, good purpose, is quite likely in class number 1. It's somewhat likely also in class number 2, but it's very unlikely in class number 3. The next row, I multiply the probability of the pattern by the class proportion, by the cluster size. This number times this number, and I do that for all the classes. And then I need to obtain the probability of a pattern, which is basically the sum of these 3 numbers. You can see the sum. And finally, if I divide the, let's say, the numerator of the equation of the posterior membership probability by the denominator, I get the posterior membership probability. And you can verify that. That the posterior membership probabilities that I computed with a spreadsheet are identical to the posterior membership probability reported by LatentGOLD. So you see the classification output for different patterns, and you see the computation that's also on the overhead sheet. Now let's have a look at classification statistics. And so I indicated that we can compute the posterior membership probabilities and check which one, for which class it is largest, and then we can say, well, let's assign a person to that class, let's classify the person into that class. But how well are we doing when assigning individuals to latent classes? In other words, how well can we predict a person's class membership based on the observed indicators? Because that's what we basically are doing. We're using the observed indicator scores to determine to which class a person belongs to. There's three types of statistics that can be used for this purpose. The simplest one is just computing the proportion of classification errors, the estimated proportion of classification errors. It is also possible to compute a classification table, and the third type of statistic is the so-called pseudo Rsquare measures. It's similar to an R-square, but based on classification errors, entropy, or qualitative variance. I'm going to discuss these three types of statistics. Let's first look at classification errors, the proportion of classification errors. For each individual, we can compute 1 minus the maximum of the posterior probability. Let's say 1 minus the probability associated with the model class. And we can average that number, 1 minus the maximum of the posterior, over individuals. If we do so, then we get a value of 0.1533 for this data example. In a minute I will show you in a spreadsheet in more concrete how this works. In addition, we can compute a classification table which looks like this. Yes, in the LatentGOLD output you get this table. And it's a classification of, on the one hand, the true class membership and the model assignment. So you can see that among the people which is assigned to cluster number 1, so 964 people would be assigned to cluster number 1, and it's estimated that out of those persons, 841 really belong to cluster number 1. So this is the classification errors that you make. And actually what you see on the diagonal, the numbers, are the correct classifications, and off diagonal you see the classification errors. So if you sum the frequencies in the off diagonals and divide by the total number of persons, you would again get this 0.1533. So actually the classification table gives more information on what kind of error do you make in the classification. But let's go to the spreadsheets in which I show how to compute those numbers. To compute this number and how to get this classification table. What I did in this spreadsheet is that I copied the classification output from LatentGOLD. So you have seen the classification output from LatentGOLD, but I've modified it slightly to make it slightly more compact. So I changed from value labels to values for the variables. Well, how do we obtain the classification errors, as I indicated? So this is the posterior membership probabilities for each pattern. So what I'm doing here is I say 1 minus the maximum of these. So that's the proportion of classification errors that you make for this pattern. There is in total 535 people within this pattern. So you could say the total number of errors is 0.1152 times that frequency. So I multiply the error, let's say, that I make for one individual by the number of individuals. Well, this is done for all patterns. Here I take the maximum from this row, multiply by the number of persons with that pattern. This is done for all the patterns. I sum over all the patterns. and divide by the sample size, which is 1644. And then you see the number popping up here. The proportion of classification errors, the estimated proportion of classification errors is 0.1533. So now let's look at the classification table. I'm not going to compute the full table. What I will do is compute, I'm going to the output, I'm going to compute the first column of this table. And so the column corresponding to the persons assigned to cluster number 1. So what I need to do is select the records of persons or the patterns which are assigned to cluster number 1. And so let's see how the formula looks like. So I select with the if statement the records which let's say belong to cluster number 1. And what I do is I multiply the probability that those persons are assigned to cluster number 1 and multiply by the total number of persons with that pattern. And so basically I'm going to count in this first column the probabilities of being in cluster 1, cluster 2 and 3 for those who are assigned to the model cluster number 1. And if I count in these probabilities for a particular person, for a single person, then I have to multiply by the number of persons with that pattern to know, let's say, how much in total I should count in. And so then you see, let's say, these numbers appearing. So this is, let's say, what I will add to the first column for the very first pattern. Now for the second pattern, it's also a pattern which is assigned to the model cluster number 1. I have these frequencies that are counted in, etc. Well, the patterns which are not assigned to cluster number 1 get a 0, so they kind of cancel out at the moment that I'm going to compute the sum. And so what I'm doing here is I'm summing the results in the first column, I'm summing the result in the second column, etc. And we can confirm that these numbers are the same. Well, it's a bit, let's see if I can show this. Oops. So you can see the numbers that you obtain here are the same as those appearing in the classification table. Well, similar thing can be done for the second and the third cluster. So if you can do that yourself if you would like to do so. But then you have to select the patterns that are assigned to cluster number 2 and then the ones which are assigned to cluster number 3. So this concludes the first two types of classification statistics, the proportion of classification errors and the classification table. Let's look now at the pseudo R-square measures. And basically what these pseudo R-square measures do, they compare the prediction of class membership based on only the cluster proportions with the prediction based on the probability of being in a certain class conditional on the responses, using the posterior class membership probabilities. And so you want to see how much better can you predict the class membership if you use information on the responses compared to the situation in which you don't use information on the responses, if you don't know anything about the person. And the general formula of a pseudo R-square is that you compare the loss of this predicting the class membership without information on the responses with the loss that you obtain if you use information on the responses. So this is the difference, and then you divide by the loss that you had without using information on the responses. You can, let's say, call this the proportional reduction in loss or the proportional reduction in errors. You can also write this as 1 minus the loss conditional on the response divided by the loss overall, let's say without conditioning. And so this is a very general idea that we're going to apply here to latent class analysis, but you can apply that to let's say more in general in prediction situations. The proportional reduction in errors, the proportional reduction in loss. The loss that we use here can be the proportion of classification errors. We already saw that the proportion of classification errors is 0.1533. We can compare this number of 0.1533 with the loss that we would have if we don't use the responses. And the pseudo R-square resulting from using classification errors as a loss function is sometimes referred to as lambda. That's also how it's called in the LatentGOLD output. You can also use as a loss a quantity which is called entropy, the average entropy, and I will explain in a minute how that looks like. And you can also use the average qualitative variance. And there's other loss definition that you could use, but those are the three implemented in LatentGOLD for this purpose. The entropy is a quantity obtained by summing the probability times the logarithm of the probability, or actually the negative of the probability times the logarithm of the probability over categories, in this case over latent classes. In qualitative variance is 1 minus the sum over classes or over categories of the square of the probability. I will show that in more detail in the spreadsheet that I created. But let's first look at the pseudo R-square based on classification errors. And so we already saw that the proportion of classification errors is 0.1533. The proportion of classification errors that we make at the moment that we use the information on the responses to predict the class membership. But what's the proportion of classification errors that we obtain if we don't have information on the responses, if we don't use information on the responses? Well, if you look at the profile output, you can see that cluster number 1 is by far the largest cluster. So if you don't have information on the responses and you would use the modal class assignment rule, you would say, well, all the persons belong to cluster number 1. And if you do so, the proportion classification errors is 1 minus the maximum of the cluster proportions, which is 1 minus 0.5677. And so that's actually the loss in the prediction of X if you don't use the responses. So that's what I do here. So I have here the cluster proportions, and they say 1 minus the maximum. So that's the loss that you have if you don't use information on the responses. And then I apply the formula, namely the overall loss minus the loss when using the response divided by the overall loss. And you get a number kind of similar to an R-square, a number between 0 and 1, indicating how well the prediction is. It's 0.65, rounded 0.65 or 0.6453. And that, if you look at the LatentGOLD outputs, so we see the classification statistics outputs. Classification errors is 0.1533, and the reduction of errors called lambda is 0.6453. That's exactly the same number that we obtained in the spreadsheet. Now let's go to entropy. Entropy is basically a measure to indicate how different those probabilities are. So in the case that one probability is equal to 1 and the other ones are equal to 0, and then the entropy will be 0, which is comparable, let's say, to making no prediction error, if the prediction error is then 0. And entropy is a different way of expressing, let's say, how different the probabilities are. So you don't take 1 minus the maximum, but actually use all of the three the probabilities, let's say, to get a number which is equal to 1 in the case of perfect prediction and is not equal to 1, it's even larger. Sorry, it's equal to 0 in the case of perfect prediction, and is larger than 0 and more larger than 0 at the moment that the prediction becomes worse. So let's look at the formula. I already showed the formula on the transparency. And you can see I take minus the probability times the logarithm of the probability. And so I do that for every cluster, cluster 1, 2, and 3, and I add it up over the clusters. So I take the sum of minus the probability times the log of the probability for all the categories, and I sum it. Well, I want to compute the average of this thing across all patterns. Well, how do you compute the average? You multiply this thing by the number of people with the pattern. Do this for all the patterns. Sum. And so this is the total entropy. If I'm right, it's also reported by the program. It's one of the items. And if I divide by the sample size, I get the entropy obtained, let's say, by when predicting the class membership using the responses. So what's the entropy that I obtain if I don't use the responses? Then I have to go to the class proportions, the overall class sizes. So I have to compute the entropy for those. So what I do here is I compute the entropy using here you see again this formula minus the probability times the logarithm of the probability, but now using the overall cluster proportion. I do that for all clusters, add it up, and then I get let's say the total entropy, or the entropy that you obtain if you don't use the responses for classifying individuals. And then again, this is the loss given the y's. This is the loss without using the y's, and this is then the pseudo R-square based on the entropy, and the entropy based R-square. Well, a similar thing can be done with another quantity, which is called qualitative variance. And it's a kind of extension of a variance to the situation in which the variable that you want to predict is a nominal variable. It's not a quantitative variable, but a nominal variable. And the formula, I already showed you the formula. It's 1 minus the sum of the squared probabilities. So what I do here is that I square the posterior probability for cluster number 1, for cluster number 2, and for cluster number 3. And here you see 1 minus the sum of those. So this is actually the contribution to the qualitative variance of an observation belonging to the first pattern. Well, again, I have to compute now the average over all individuals in the sample. So I multiply this number by the total number of persons with that pattern. I do that for do the computation, let's say, for all the patterns. Compute the total by summing the numbers in this column and dividing by the sample size. And so in terms of qualitative variance, the loss is 0.2420 if I use the responses to predict class membership. And if I don't use the responses to predict class membership, well, I can do the same computation, but now with the overall class proportions. Then the number is the sum, 1 minus the sum, and these are then the squared class sizes. So then the loss is 0.5802. Again, applying the general formula for pseudo R-square yields a value of 0.583. And as you can see, these are the numbers for the entropy R-square and the standard R-square reported by the program. So here I summarize the computations based, let's say, on the value of the loss functions that we obtained. So here I apply, let's say, the general definition of the pseudo R-square, right? You obtain the lambda entropy R-squared, and in the program we say standard R-square, but it is actually a modification of a standard R-square to be able to deal with nominal variables. The most popular of these is the entropy R-square. So most applications or most articles on latent class analysis, people will report the entropy R-square. And if you go to the LatentGOLD output, you will see that in the summary table, we reported the classification errors, 4% classification errors, and the entropy R-square. Well, how would you interpret the value of 0.55? That's what we call a moderate quality prediction. So if you go, let's say below 0.40, then it becomes really bad. If you are above 0.8, then you have a very good prediction, and this is a kind of intermediate value, so it's a kind of moderate prediction. And it's a too low value if you really want to be really, let's say, certain about the class membership of an individual, but for other applications it may be good enough. Well, a final remark is that classifications can also be written to an output file. And this is especially relevant if you want to use that applications later on in further analysis. And this shows the classification prediction tab in LatentGOLD. And I will go to LatentGOLD and show you how this works. So if you go to the classification prediction tab in LatentGOLD, you can say, well, I want to write a classification and predictions to an output file. We use the classification posterior option here. You can put in a name of a data file and indicate which other variables you would like to keep in the data file that is created. And then you say estimate. And now LatentGOLD has created a data file where the classification information is appended. The final thing I will do is, let's say, open this file to show you how it looks like. So here you see the original data file, the original variables, and there is 4 columns added, namely the probability between cluster 1, cluster number 2, and cluster number 3, and they are called cluster 1, cluster 2, cluster 3, and you have the model cluster assignment. Well, this concludes this video on classification and classification statistics.